Hey everybody, it's Mr. Klein in a hat, definitely fun. And today we're going to be talking about something called the chain rule, or as I like to call it, the chain of rules. So anyway, here's the idea for the chain rule. You use the chain rule when you have something that is called a composite function. A composite function is any function where you have an inside and then you have a different outside. So for instance, the function that you see right here is the composite of something cubed and x squared plus 1. Now, I'm going to start by doing this one the non-chain rule way, the kind of painful way, and that's by expanding it first. So if we wanted to expand this, we would say, well, it's to the third power, and so let's see, Pascal's triangle, the third row, or the row with the threes in it at least, is 1, 3, 3, 1. So we could rewrite this as 1 plus 3 plus 3 plus 1. And then we could say, I've got x squared here. So this will be x squared to the third power, x squared squared, x squared to the first, and x squared to the nada. And then I got a 1, so it'll be 1 to the 0, 1 to the 1, 1 to the 2, 1 to the 3. And all of that simplifies down to x to the 6th plus 3x to the 4th plus 3x squared plus 1. The derivative of which, I'm feeling lazy, so I'm just going to call it y prime, would be, using the power rule, 6x to the 5th plus 12x to the 3rd plus 6x. All right, so there's our answer. Now, I'm looking at that answer and I'm thinking to myself, I think we could factor that, right? Couldn't we factor that? What could we factor out of it? Well, we could factor out 6. And we could also factor out an x, and that would leave us with x to the 4th plus 2x squared plus 1. Ooh, and now I'm thinking to myself, look at what we've got right here. Doesn't that factor as well? What would that factor to? So a result is 6x, x squared plus 1 times x squared plus 1, which we really should write as 6x, x squared plus 1 squared. So there is our final answer. Now, look at that. Oh, that was cool. It made a parallelogram. Now, look at the final answer and then look at where we started. What do you notice about the inside function? It's the same, right? What we have here is what we have here. What else should we notice? We had a degree on the original function, and that degree has gone down by 1. The only thing that's kind of weird is that we've got this 6x here. Let's figure out where that came from. I'm now going to teach you something called the chain rule. All right, this is going to take a little bit of setup. I want to start by defining the inside function. So let's call the, I don't like these colors. Let's change color. Let's make this black. All right. So let's say that the inside function of y equals x squared plus 1 to the 3rd power. By the way, these notes are in your Unit 4 note packet. You should bust that out. If you don't have it, you can print it off of Canvas. Let's say that the inside function, we're going to call that u. Why? Because I like u. So I'm going to say that u is x squared plus 1. In other words, we've redefined this. And if that's the case, then we can say that y is just the inside function cubed. So it would be u cubed. Now, using what we've got right here, we can come up with two derivatives. We can say the rate of change of the u function with respect to x, because x is our variable right here, would be equal to 2x. And we can also say that the derivative of our y variable with respect to u, because u is our variable in the second equation, would be equal to 3 times u squared. But let's keep in mind that neither this nor this are what we're looking for. What we want is the derivative of y with respect to x. So how do we get that? Well, let me scooch down the page a little bit. We want this. That's our goal. I'm going to suggest that we can break that up into a chain of derivatives. And by a chain of derivatives, what I mean is two or more derivatives that have been multiplied together. And you can basically use algebra to think about this. You can say dy over dx. I can write the dy here. I can write the dx here. And that leaves us with two spaces, one here and one here. And we can fill those spaces with whatever we want as long as they're the same thing, so they cancel out. Well, based on what you saw up here, what's our only choice? Isn't it du? Well, check this out. Put du here, and I put du here. Now we're saying that the derivative we want, dy dx, will be equal to taking dy du. Let's see, what was that equal to? That was 3u squared. And multiplying it by the derivative of u with respect to x, which was 2x. And recall that u is defined as something else. So I'm going to rewrite this expression. I'm going to leave a space for u. And let's recall that u was originally x squared plus 1. Well, look at what we have here, folks. 3 times 2x would be 6x multiplying x squared plus 1 squared. And so, ladies and gentlemen, I give you an answer that is the exact same as what we got when we did this the long way upstairs, which is cool. All right, so this is called the chain rule. A couple things I want to mention to you. One is that you can make the chain as long as you want. So we could say dy dx is equal to, put a dy here and a dx here, and we could just keep filling stuff up in, like dA, district attorney, or dB, David Bowie, or DC, District of Columbia, DD, Dungeons and Dragons. It doesn't matter as long as you have cancellations here and here and here and here that will eventually simplify your expression back to dy dx. So the point is that we can have a chain that's longer than just two derivatives multiplied together. The other thing that I want to mention to you is that you're going to see this notation quite a bit. This is composite function notation, f of g of x. So let's suppose that h is equal to f of g of x. We could write the derivative expression this way. If you go back to what we did above, the first derivative, I should have written this down before, this is worth noting. This one right here was the derivative of the something cubed. So this is the derivative of the outside. And then the second right here was the derivative of the inside. Which means that we could write this expression as, let's see, outside function is f prime of something. And then what do we write for that something? Well, let's go back and look. Seems to me that up here, the thing that ended up inside was the same inside that we had originally right here. So the inside gets left alone, which means this will be g of x. And then the second one is to take the derivative of the inside. So this will be g prime of x. There's a formula. Know it, live it, love it. Have it in your brain. Let's do some examples. Okay, these you can write down on a separate sheet of paper as we go through them. I need a color. Let's pick a color here. Yellow is too. We'll go orange. Okay. So f of x is equal to the cosine of 3x. First thing you say to yourself is, do I have an inside and an outside function? Yes. What is the inside function? 3x. What is the outside function? Cosine of something. Inside, outside. Next step. Since we have an inside and an outside function, I know that the result is going to be the product of two derivatives. The first one is the derivative of the outside. So we say, what is the derivative of cosine? The answer is negative sine. Of, you leave the inside alone. So we rewrite the 3x. Multiplied by the derivative of the inside. Since the inside is 3x, its derivative will be 3. I would like you to write your final answer this way. Coefficients come up front, so we get negative 3 sine of 3x. And there is our answer. Next one. Y is equal to the cosine cubed of x. Now, funny thing about math notation on this one, that 3 right there is kind of tricky. The 3 is the outside function, because what this really means is something cubed, where that something is cosine x. So this time, our inside is cosine x, and our outside is something cubed. So that was the first step. Identify your inside and your outside. Second step is to take the derivative. This is a y, so I'm going to write dy dx equals, I see two functions here, so it's going to be something multiplied by something. Outside function is something cubed. What is the derivative of something cubed? We get 3 times something squared. What is that something? You leave the inside alone. So a good rule is that only one derivative happens in each step. In this first step, the derivative that happens is the outside. Since the outside was something cubed, I only did 3 times something squared. I didn't do anything to the inside. We'll do something to the inside now. Second step is, what is the derivative of cosine? And that is negative sine of x. Therefore, our best final answer would be to say the derivative equation is, move the negative up, negative 3 cosine squared x multiplied by sine of x. Woo! Let's keep moving. Next one. On the next one, I see a sine and I see a cubed. What is the inside function? What is the outside function? Well, the inside function is here, and the outside function is here. So we've got our inside and our outside. And I only see 2 steps here. So when I take the derivative, I want to have something multiplied by something. So we start with the outside. The outside is sine. The derivative of sine is cosine. I'm going to make a mistake here. You tell me what my mistake is. That's right. You only take 1 derivative in each step. So this should be left alone. We just take the derivative of the outside in this step. In the second step, we'll say the inside is theta cubed. So the derivative will be 3 theta squared. 3 theta squared, that's a nice little circle or oval, whatever you want to call it. That's a power function. When you write your final answers, I want you to put power functions first. So before trig, so we would write this one as 3 theta squared times the cosine of theta cubed. That would be our best final answer. Now let me come back to the original problem for just a second. Let's suppose that I stuck 5, one of my favorite numbers, in front here. What would that do to the rest of the problem? The answer is it would just multiply it by 5. So if you see a coefficient here, that coefficient would continue to be here. And then in the last step, it would end up getting multiplied by the 3. And we would get a 15. So if you see coefficients, they're just along for the ride. They don't do anything. Next one. All right. Now we're getting into problems where you need to manipulate the expression before you can take the derivative. We don't know how to deal with denominators yet. So what you're going to do on a problem like this is you're going to take this denominator and you're going to move it upstairs. When you move it upstairs, the 5 is chilling. The rest of the function goes to the -1 power. So the problem is now going to look a little something like this. I know that sine to the -1 is cosecant, but since we don't know how to deal with cosecants, we're just going to leave it in this format for the moment. Now this one's a little trickier because what I see is that we have an inside function right here. We have a middle function right here. And then we have an outside function right here. So this problem has 1, 2, 3 different functions going on. The 5 is just along for the ride. Now, since there are 3 of them, when I write my chain rule, I'm going to say that the derivative of t is equal to 5 is just along for the ride, so I'm going to put a 5 in front. But then I'm going to multiply it by 1, 2, 3 things, where the first one is the outside, the second one is the middle, and the third one is the inside. Let's start with the outside. The outside is something to the negative 1 power. What is the derivative of something to the negative 1 power? Negative 1 times something to the negative 2. Take whatever that something is on the inside, write it. Step 2, look at the middle. The middle is sine of something. What would be the derivative of sine of something? Cosine of something, where that something is 3t. Now we're almost done, but we're not done. The last step is to take the derivative of the inside. The inside is 3t. The derivative of 3t would be 3, which means that this one works out to be, got to clean this up a little bit. I see a 5, negative 1, and a 3. There's 3 coefficients. We're going to put those together, and in the numerator, that's going to give us a negative 15. Also in the numerator is the cosine of 3t right here. This one's going to have a denominator. Notice that here we have an expression that is to the negative 2. I'm going to take that and move that down so that it becomes the sine squared. Notice we got a positive exponent now of 3t. And trig-wise, you could probably play around with this guy a little bit. But the way we got the answer right now is perfectly good. Let's leave it at that. One more. Last one is the cube root of 5x squared plus x plus 7. So on this one, I see an outer function that is cube root. Now, it might be worthwhile to rewrite that as something to the 1/3 power. I see an inner function of 5x cubed plus x plus 7. So our derivative is going to have 2 chunks. First one is something to the 1/3. What is the derivative of something to the 1/3? Okay, what do we put inside? Multiplied by the inside function has a derivative of, let's see, the derivative of this would be 10x. The derivative of this would be 1. Final answer for this one. In the numerator, we have this 1 right here and this 10x plus 1. So that would give us just 10x plus 1. In the denominator, we have a 3 multiplied by 5x squared plus x plus 7, all to the 2/3 power. And there is your final answer. All right, you try some. Try this example right here. All right, check your work. 7 is along for the ride. Sine is the outside function. Derivative is cosine. Leave the 5x alone. Inside function is 5x. Derivative is 5. Your final answer looks like this. Try the next one on your own. All right, check your work on this one. This one's a little trickier because it has 1, 2, 3 layers to it. The outer function is something to the 4th. So you get 4 times something cubed. That something is cosine 3x. Your middle function is cosine. The derivative of that is negative sine. Leave the 3x alone. Innermost function is 3x. The derivative is 3. Your final answer should look like this. Negative 12 cosine to the 3rd 3x sine of 3x. Try this one on your own. All right, check your work on this one. This one has 2 layers, so we should have 2 things multiplied together. Outer function is something to the half, so the derivative is 1/2 something to the negative half. Inside is 9 squared minus 7. Derivative of the inside would be 18t. Final answer looks like this. Cancel the 2 with the 18. That's going to leave you with a 9t in the numerator, square root of 9t squared minus 7 in the denominator. Why in the denominator? Because we take that negative and we move it down.